So we now turn to another application of the calculus of residues, which is to sum certain types of infinite series. So again, this seems rather like the integration techniques we did. It seems rather magical that it should work. But basically, there's in fact four formulae. This is the first of four. Basically says if you've got some function of n and f of z contains a finite number of poles, this rule could actually be bent, but we'll not go into that in this at the moment. If f contains a finite number of poles at zj, and importantly, z times f needs to go to 0 as for large z, large mod z. Then it turns out the sum of fn from n goes to minus infinity to infinity, but not including any n which coincides with the poles of f, is equal to this sum of the residues of f times cot pi z. So it does seem rather magical formula. Okay, so I'll sketch how to do this. You can read the notes in detail to get the full picture. Okay, so the idea is we use this kind of contour. It's a square contour. And we're considering this contour in this integrand. So we've got cot pi z. So if we've got cot pi z, well, obviously cot pi z is going to, well, if you think of it, it's 1 over tan. So when does tan have singularities? Well, it's when, okay, sorry, when is tan 0? So tan is 0 when tan z is 0 when z is 0, and it's period pi. So it's 0, it's multiples of pi. So if you got tan pi z has zeros at the positive integers, at all the integers, which means that 1 over tan pi z or cot pi z will have poles, simple poles, at all of the integers. So that's what we've got here. So automatically you're going to have poles at all of the integers. If we try and integrate this fz times pi cot pi z. Of course, f of z could also have some poles, but we don't know where they are unless we specify what z is. Okay, so the contour integral is a square. The reason for choosing this n plus a half is simply so that we don't integrate through a pole. That's all. And just for convenience, we make it a square. The important thing is that this is n plus a half and this is minus n plus a half. And we just choose to make it a square contour. So we then take the limit as n goes to infinity, but we always make sure we don't integrate through a pole. So n stays as an integer, but it gets larger and larger. So what we actually need to show is that the integral along these 4 lines goes to 0 as n goes to infinity. So I'm not going to talk about that now, you can read it in the notes. So we end up with this thing equaling 0, but of course also this is equal to this 2 pi I times the sum of the residues of this function. So as this goes to infinity, we'll actually have an infinite number of poles. So we sum over that infinite number of poles, and effectively that generates this sum here. So we'll see how that works. Okay, so all this paragraph was just arguing that the integral along these 4 lines is 0. So now we apply the residue theorem to this equation here. Now we've shown that the integral is 0. Okay, so as we just said, pi cot pi z has simple poles at all of the integers. And the residue in each case is 1. Okay, so to see that, why is the residue 1? Well, remember, cot pi z is cos pi z over sine pi z. So if we use the p over q dash rule, then our q is sine. Differentiate sine pi z, we get pi cos pi z, and that exactly cancels the pi cos pi z on the top. So we get a residue of 1. So that means that if f of z does not have a pole at a particular value of z equaling n, then what's the residue of fz pi cot pi z? Well, we've just said the residue at that integer is always going to be 1, coming from just the pi cot pi z. Now we've got f of z where z is not at, there's no singularity of f at that particular value of n. So we just get left with f of n, because this is just gives you 1. So just substitute z equals n and get f of n. So the residue at that point is therefore f of n. So basically, if there is a pole at z equals n, then we have to evaluate the residue at that point, which is this. If there's no pole, then we just end up with f of n. So applying the residue theorem, the integral is equal to 0, and we've got 2 pi I times the sum of all the residues. So there's the bit where there's no problem, where the pole of f of z doesn't coincide with a pole of pi cot pi z. That gives us the sum of fn. And then we also get where the pole of f of z does coincide with an integer, and that's what we're summing here. So if we then rearrange this and take out this factor of pi here, we end up with this equation here. Okay, so there's another formula. The second of the 4 formulae is this one here. The only difference is now we've got a cosec rather than a cot, and we've got minus to the n here. So we do exactly the same thing, except that rather than using pi cot pi z, we're using pi cosec pi z. It turns out that this again has simple poles at the integer values. This is fairly obvious because cosec is 1 over sine. But this time the residues, you can easily check, are minus 1 to the n rather than just 1. So we end up with this extra factor of minus 1. in here. Otherwise, the technique is exactly the same. The proof is exactly the same. Third and fourth formula of these. This is f of n plus a half. We've got tan, and the same thing, but with an extra factor of minus the n. We've got sec here. So notice all of these have poles. So now both tan and sec, of course, have poles at half integer multiples of pi. So we end up with simple poles at n plus a half. And okay, if you work out the residues at those places, you get -1, and -1 is the n plus 1. So basically, I'm happy for you to use these four formulae without deriving them at all. It's too much effort to derive them each time, so I'm just happy for you to look at the formula sheet and use these formulae. So it's fine to do that. Too much effort to derive. Okay, so it turns out as we'll soon see with examples, when you're as we've mentioned before, if you end up with a higher order pole at z equals 0, as you often do when solving these problems, it's easiest to consider the Laurent expansion. So I've just given you these expansions of the four functions you need for the four formulae. And okay, well, these expressions are also helpful just to remember the derivatives of these four trig functions. So to do an example, let's find the sum of the squares. So we obviously have f of z equal to 1 over z squared. This only has one pole at z equals 0. So you have to be careful. The only thing, well, we're asked for the sum from 1 to infinity, but the formula gives us minus infinity to infinity. Realize that it doesn't include n equals 0 because there's a pole there. So in fact, the sum we want, well, twice the sum we want is equal to the sum we get from the formula. Okay, so the formula gives us, there's just one pole, so we just need to find the residue of this thing at z equals 0, which is straightforward to do from this formula. So we have to divide by z squared and then look at the coefficient of 1 over z, which will be minus 1/3. We also obviously have this factor of pi coming in. So the residue we get is minus pi by 3. The factor of pi I'm talking about is here. We actually get this extra factor of pi, which gives us pi squared, and then divide by 2, and we get the final answer of pi squared by 6. Just to mention that if there's a parameter, you can also differentiate, as with integrals, you can differentiate sums with respect to the parameter. That's a useful trick, which I suggest you use to do this part here. It's also worth exploiting this formula, these two formulae, when you can, as in this question here.